restart because I don't like the way this is going. Sorry about that. I'll start again in a minute. Just see, I don't know what went wrong. Why I didn't want me to. Options. Laser pointer. Yeah, that's what I want. Okay, let's start again. We've got simple random sampling carrying on from last week. We're going to estimate the population mean as well as the population total, but to start off with, to take further what I said last week, you should all be very comfortable. This is exactly from the previous week's grid. With other words, we've got simple random sampling without replacement, which often is just called SRS. They don't always have this without replacement sign. And then we have simple random sampling with replacement. You know that if you're estimating the population mean, both for without replacement and with replacement, what do we use? We use sample mean. So you want to work out the average of a large data set. You take some elements into your sample using simple random sampling with replacement or simple random sampling without replacement. In both cases, you use the sample mean to estimate the population mean. You're all aware of that. Then last week I gave you this table which says if you want to calculate the variance of the estimator, remember we said that there are many different samples. The population mean is a constant, but the estimate of the population mean, remember this hat says we're estimating the population mean. We use the sample mean, as you can see. The sample mean is the estimate of the population mean, and that sample mean varies between samples. That's why it's got a variance. It's called the sampling variance of the estimator. And you can work it out like this. 1 over n, 1 minus n over n, big S squared. When you're doing that, you've got to say, well, if I want to work out the variance, I know the samples, different samples have different little means, and those means differ. That's why there's a variance. But can I work out this variance of the estimator? Can you calculate that? Well, the first thing you've got to say, well, I know little n. Yes, I know how many elements I'm selecting. Well, I know big N. You will know because you've got a whole population frame. You select from the frame, so you do know N, but you don't know big S squared. To work S squared out, you need all the wild values of the population. So you can't work out big S squared. And so you cannot ever find that when you're doing without replacement, and similarly with replacement, you can't find that either. So what do? We estimate the variance. And we do it exactly the same way, but the big S squared gets replaced by a little s squared. And this, if you work it out, can be written like that. I can prove it for you, but you'll just have to take my word for it at this stage. This table is what you really need to know. And it's not hard. This, you can see, if you look at this one, this is identical formula except that the n has become a 1. Can you see that? Everything else is the same. This is identical to that, but the big S became a little s. And this is just S squared over n. So if you're using without replacement, with other words, you're selecting n elements from the population of size big N, you take one, and now it's out the population. You had n values, you took the first one. When you took the next one, you had n minus 1 values in the population because you didn't replace until you've got your n values. In the with replacement, it's the same. You randomly select, but you replace each time. Okay. Now, the first question I could ask you, and you said I must give you some clue about the type of questions, just in your logic. Would you think without and with replacement are ever sort of similar? Imagine if your population size is huge. I've got 10 million people and I'm picking 4. When you replace that person, do you think it's going to make much difference? This population is so huge and you're just picking a few. Whether you replace or not, it's not going to make much difference. Do you agree? So there are times if your population is huge compared to your sample, with and without, just logically, should be about the same. I mean, you can see for yourself, it shouldn't make any difference really. Because, and you can see it here, whether you have N over N in your variance here, this item, N is so small compared to big N, it's almost like 1 over N. If it's 3 over 10 million, not much difference whether it's 3 or 1 out of 10 million. So that's what I'm trying to do in this course, is to show you it's not just about learning theory. You have to look at a formula and it should make sense to you. If you work this out as a decimal, and you work that out as a decimal, if this N is very, very small compared to big N, these two factors will be almost the same. And if you look at these two variances, they're almost identical there. They'll be almost identical. So that's actually saying, but hang on, this is the same as that, this is the same as that. What makes it, whether you're doing without or with, the variance of the estimator is roughly the same. But that's obvious if you think logically. In a very large population, you pick few elements, whether you replace or not. Thank you. Okay, so are we all clear on that? Now the next thing, I've just put here the formulas for the variance of the Y values, or whatever your reading is of interest that you're trying to estimate about. For the population is the S squared one, as well as the sample one, which you can see here. Now you can look again at this formula, 1 over n, 1 minus n over n, big S squared. I do know small n. I know how many elements I'm going to pick if I'm doing simple random sampling without replacement. I will know little n, I will know big N. Now I need to find S squared. But look at S squared formula. If you don't know the population, you only know the sample's Y values. Because you interview people or whatever, you measure their height. You might know the person's name and his ID number, but you don't know how tall he is. You're going to take the sample and measure people, if you like. Those will be your Y values. So no one can work this out because you don't have the whole population's values. So that is why this is the thing you can calculate. Now, if you look at the estimated variance, 1 over n, 1 minus n over n, this is the case of simple random sampling without replacement. Clearly, you can work out little s squared, because look at little s squared. It's the same as big S squared. It's just the variance of the Y values. How far do the Y's on average differ from the mean? YI minus Y bar, but you're only summing through the sample. You see, it only goes up, it's only your sample Y's. That you'll know. And you can see here, these are the big set you won't know. So that is why generally, let's suppose I'm trying to estimate in the population the mean. What am I going to use? Y bar. What am I going to calculate? The variance estimated of this thing, estimated, little Y bar. This is the estimator for that. That's a constant, this is a variable. It differs between samples. This tells me how much it's going to differ, but I can't work it out because of the big S squared. This is the thing you're going to actually work out. Can you see that? And exactly the same again for with replacement. Okay, with replacement, all the same stories, but it's this lot of stuff. Are you all clear? Estimating theta is T is in Y bar. Why do we say that? I'm now estimating not the population's mean, but the population total. What is the total number of children under the age of 5 of all employees at UKZN? We want to have a Christmas party. We want to know how many there are. So we're trying to estimate that by taking a few of the staff members. We wouldn't on the staff data know how many children they've got under the age of 5. It keeps changing, right? People don't tell you when they've had a baby. So what they're doing, they're saying, we want to have a Christmas party at UKZN, for example. We want to see how many people will be coming. We sample a lot of the staff, and we see how many children they've got. We ask them. We record that, and we try and use that to estimate for the whole staff, based on what I found out in my sample, in total, how many children are under the age of 5, and what can you say then about the total number of children under the age of 5 of the population? Because remember, our theta is the population value. I'm interested in estimating the total, whatever the total is. And here they say this is how you always do it. If you want to estimate, this is only for simple random sampling. Other Other samplings are going to say, you want to estimate the population total, it's a totally different formula. In simple random sampling, whether it's with or without replacement, you estimate the mean by Y bar. Now they're saying, you know how to estimate Y bar, you just look here. Everything is here. So if you want to estimate the total, isn't the total in Y bar? How do you know that? How would you work out the mean of the whole population? You take the total and you divide by N, right? What is the mean? It's the total divided by N. So if you want to know what the total is, it's obviously in Y bar. Okay, just work backwards. That's the kind of thing you shouldn't, you know how to estimate, you work with Y bar, you want the total, you just go in Y bar. So now, similarly, I'll put a table together for you to know exactly the same way. I now don't want to estimate Y bar, I'm rather estimating the total. So the hat is there, I'm interested in estimating the total. Maybe I'm going to do without replacement and maybe I'm going to do with replacement. If you know how to estimate Y bar, won't you know how to estimate in Y bar? Because N is just how many people are in your population. And you've got a sampling frame. You can see I've got a list of, say, 620 people in my frame. I'm going to pick 45, say. You've got to know how many people there are so that you can contact whoever you've chosen. So N you will know. So we already know how to estimate Y bar because we can look here. If I'm doing without replacement and with replacement, to estimate Y bar, the estimate is the same, but the variance is different. So now you say, okay, I want to estimate that. How do you estimate the total? Well, it's not hard. I know it's N Y bar, and to get the N is a constant. That's the first thing you must remember. The N is how many people are in your population. That's a constant. So now I want to estimate N Y bar. I can put N down, so I'm trying to estimate Y bar. I'll know N. It's on my sampling frame. Now I want to know Y bar, but Y bar, to estimate it, I use that. So obviously, you estimate this by N little Y bar. Similarly, if I'm doing with replacement, it'll also be N Y bar. Then I want to get the variance of this N Y bar. You know what the variance of Y bar is? Here it is. 1 over N, 1 minus N over N S squared. Can you see it's here? 1 over N, 1 minus. It's all the same. That part is identical to that. But when you say variance of T hat, I want to know what's the variance. This is T hat. How much does N Y bar vary? Variance of N Y bar will be N squared variance of Y bar, won't it? Because N is a constant. So it's N squared and the variance of Y bar comes here. Can you see where that comes from? Is there anybody that's not clear? N is a constant. You know it. How many people in the population? You know how to get the variance of Y bar. It's here. So variance of this will be N squared variance Y bar, and you just look next door. How would you find the, similarly, we already know the estimated variance. So it will just be the estimated variance. You want to know, how do I estimate that? Well, we already know this thing gets estimated like that, so it's just the N squared in front. And you see that if you know this, this follows immediately. If you know Y bar, you know everything about T. And then similarly, I'm doing with replacement now, not without replacement. You estimate it. We said estimating T is N Y bar. I estimate the Y bar in with replacement. I estimate it with a little Y bar, and the N is a constant, it just goes in front. So similarly, the variance here, you're just going to have the N squared coming in. Because obviously, it's the variance of this. So it's N squared variance of Y bar for with replacement. Here it is. Exactly the same thing. What do you think the next one will be? Obviously N squared, but I've got 1 over N and then a S squared. I've got a 1 over N twice. One of these must go out. I'll correct it in my, can you see that is N squared over N? Yeah, that N squared shouldn't be there. Okay, that one should be like that, but I will correct it and put it up on the slides. So now next we want to look at, so can you see this previous slide? It's a very, very important slide. When you look at printouts of computer program where you got results, you should have a clear head about these two things. That won't take a long time to do. to understand it, but we keep using them. Even when we do stratification, we're going to use these results. This is sort of the baseline, the most important results that you will do, because the others come off. The simple random sampling is often the baseline that we use to do stratified sampling. You stratify and then you do simple random sampling within each stratum. So knowing these, very, very important. So let's next talk about the confidence intervals for estimates. You know that you're 95% sure that your theta is between theta hat plus or minus 1.96 roughly 2 times the standard error, which is the square root of the variance. But we don't know the variance, so we're going to estimate it. Okay? Now all you have to do, look at the previous one. If the thing you're estimating, the theta, if your theta is y bar, it's theta hat plus or minus twice square root of the variance. So all you're going to say is that's theta hat. If it's a y bar, that's the estimate, plus or minus twice square root of that. Can you see? If I'm doing simple random sampling without replacement, with replacement, and I'm working with estimating the total, I'll use the estimate n y bar plus or minus twice square root of this with that n gone. Are you with me? So we're just going to look back at the previous table. Bearing in mind that your sample, you've got your whole sample, you can work out the sample mean, and you can work out the S squared as we have it there, the variance of the values within your sample. Those are just standard values. And now we're going to say, what are these confidence intervals? Suppose I'm estimating the population mean. What do? From the previous slide, you know that if you're doing without replacement, your estimate, your y bar hat is little, so your theta hat, your theta is y bar. What estimates your population mean? It's the sample mean. Plus or minus twice square root variance. If you look back at the previous slide, this variance, this is exactly what we say the variance is. 1 over n, 1 minus n over n is squared. But it's estimated variance. You see this hat here. So you take the estimate plus or minus twice the square root of that one. It's really very straight from the previous one. Similarly, if you want to look at the confidence interval for the population mean using simple random sampling with replacement, again, the sample mean is the estimate plus or minus twice, and the previous table I had for estimating the mean using with replacement was just S squared over n. And then we can do exactly the same, but now we've got total, not the mean. I'm estimating the total. If I'm doing without replacement, what do you think is going to happen? It will be your total is an element, not of y bar, but n y bar. So it will be n y bar plus or minus twice, same formula with the n squared. And this just works off that grid I've just shown you. And then similarly, exactly there, and this time I've got it right, 1n at the bottom. Can you see that this slide, if you compare it with the previous slide, it comes off exactly the same. So we can easily calculate whether we're estimating the mean or the total of a population. We know how to calculate the point estimate. What is the point estimate? That'll just be, if I'm doing without replacement, you want to estimate the population mean, and you're drawing n values using without replacement simple random sampling. That's the point estimate, y bar. The point estimate, if I'm estimating the total, is n y bar. But if you don't want the point, you want a whole interval, you use this for 95% certainty. These parts at the side. So that just says this is in the middle and then how far to go. Okay, are you clear on that? Please stop if you have any questions. Stop me. To demonstrate now, I'm going to give you an example. As I said, once you've got the clear understanding, and I do expect you to go through the slides. I'll put the slides up. I will later put the videos up, but I fear that if I just put the videos up, people won't come. So you can't just look at the video. You really should be here as well. So I just want you to see the example here. What it is, and I'm going to do an example, then later when you're going to get a problem, but you'll get a printout. And then you'll know where these things come from and what we're trying to do. So what we're trying to do here in this particular demonstration, you've already got law chapter 2 and with lots of comments. As I said, you don't have to go through all the other parts. But if something is here and I'll refer to it and you need more reading, you can go and read more about it. But basically, you can see here, they're talking about a population of size 3078. It's to do with farming, and they're trying to estimate how many areas with the farming land, how much is under a particular type of, how many acres have a particular type of farming, and so on. So what they do is they draw a sample of 300, and they investigate those 300 farms, how much of the farm has got corn, whatever they're interested in, and then they're going to make a decision from there. And this book, which is quite nice, they keep using the same example of 3078 farms, and you're drawing 300. So you can see here what they say, I want a simple random sampling of size 300 drawn from 3078 farming areas. It's actually farming counties. I don't really want to go into the long story of it. But what you need to understand is 3078 farms, think of it as farms, and they're taking 300 out. Because they want to estimate something about the 3078. But they don't have time or capacity to go to each of the 3078 farms and go and speak to the farmer and say, let's work out how much of your farm you're using for farming and how much you're not using. They don't have time for that. So they're only going to go to 300 farms. So the first question is, and that's something you must know, for example, the test, what is the sampling fraction? The sampling fraction, we know the 3078, and they said 0.097 of the population was sampled, clearly. Now they say SRS, that means without replacement. If you don't say WR, you know it means without replacement. So they did that, and now they said really 0.09, it's nearly like 0.1, isn't it? 9.7%. So roughly 1 in every 10 farms. You should be able to, if somebody gives you something like that, change it to sampling 1 in 10. I don't just want to know the fraction is 0.01. Say you work out a fraction is 0.08. You should be able to say that means roughly 1 in every so many farms. Like 0.097, if I say to you, talk about your sampling, you say, I sampled the fraction 0.097. Does that mean the same as I sampled 1 out of every 10, roughly? You see, you must use the language that everyday people speak in. If you just speak to think of it as explaining to a grandmother. There are a lot of things I picked 1 out of every 10. Everybody understands that. But when you say I use a sampling fraction of 0.097%, whatever, 0.097, it means nothing. And that's what you've got to learn, because we're trying to teach you that if you're the statistician in a company one day, you're not only working with lots of statisticians. If you're the statistician, you're going to work with people that aren't statisticians. So you've got to explain things in a way that even if you're not a statistician, you don't have to be able to calculate it, but you should understand what I'm telling you. So always think of it as, how can I explain this thing in a way that if you're not a statistician, I'm not trying to impress you with my huge high knowledge. I'm going to tell you what I found in a way that you can use it. Okay, so it's like that. So roughly 1 in 10. So you should think about explaining like that. So in this particular example, again, we would calculate from your sample. They use these two formulas. How would you work out the mean? Remember, your mean now is your sample mean. How many values did they take? 300 out of 3078. And from that, you can work out using that formula, this first one here. Using not 3078, that's my population. I only have values on 300. So using my 300, I'll work out with this formula, that's the mean. Work out using that formula, that's your S. The standard deviation, the square root of that variance. Did they do it with a calculator, or do you think they do it with a computer program? Obviously nowadays with computer program. So that is why when you just get a printout, you should know, oh, okay, that's not my sample because I don't know the population. That's how you should be thinking. Not can I prove it's unbiased. You just have to believe this Y bar and S actually is unbiased estimators. The unbiased estimators, the grid I've given you You know that those two grids, those are the most important things I've ever taught you. That is unbiased estimates with small variances. It's been shown, and I can prove it for you. But what do they do now? They say, now we have to calculate. I want to estimate not the mean, but the total. Why? They want to know the total in America. How much in total? We've got 3078 farming areas. What is the total amount in the country that's under agriculture? Because they want to look, we know what the total was 4 years ago. Are we having fewer and fewer producers coming through? What can we do? Is fewer and fewer of the land, people maybe are starting to say, I'm rather going to use sheep. They want to know, is it getting less and less and less people that are actually prepared to sell, to grow food and so on. So what they did, they said, we've got 3078 farming areas, let's take 300 of them and see whether the amount of land that's covered by crops, has it got less? That's really what the story is about. So you're not going to work out the average, you work out the total. But you work out the total by going in Y bar. Remember we said earlier on in one of the previous lectures, that's how we work out the total. They say, what's the average? But we already know the average. We worked it out from our 300. There it is. Multiplied by N. You know N is 3078. Can you see? So that's not hard to figure out. Don't worry about that 2.15. That just refers to, if you want to find it in the book, equation 2.15. And that's the total, the estimate now. So that's the estimated total. And the standard error, what if you go back to that table I put up earlier on, it's n squared 1 over n, 1 minus n over n, s squared. They worked out the s squared using that family, that formula. There's the s for our little n, so for the 300. You worked it out, and here it is, n squared, 3078 over little n, we chose 300, 1 minus little n over big N. Can you see where it comes from? The s is this thing, and they square it, and it calculates there. You're not going to bring a calculator to my test or my exam. I'm not going to ask you to calculate that. But you better know what it means, and you better know what formula would have been used. You're not going to physically put the numbers in, but you should know, so when you get a printout, you know where it comes from. Yes. I will show you what I will give you, for example. I will give you a basic formula. Say if I give you the formulas for Y bar. If I give you that one sheet with the Y bars, you should be able to quickly, not prove it right out, because you know T is N Y bar. And for variance, it's an N squared. So I might give you this side, and then you have that. That's probably what I'm going to do. Okay? I will talk about that at the end, but remind me on that question. It was a good question. So can you all see how simple it is? I've got the standard error, and I've got the estimate if I want to estimate T, and I use these formulas because I use simple random sampling without replacement. So I'm 95% sure that my total falls between those two. Now before we go further, if you didn't, you might just say the estimated total crops under, the estimated total land that has got crops on it is this hectares. I think it's in hectares or acres, and it's whatever that amount is. But in, remember the USA, a comma is like a space. So it's 916,927,110, whatever, acres. But this is what the answer is. But they say, no, we don't want just that answer, because we want a confidence interval that you can tell me you're 95% sure. Because if you just give an answer, even though it's an unbiased estimate, we want to say, we don't know if it's far out, but you can say I'm 95% sure it's between this and this. Okay? They don't want a point estimate, they want a confidence interval. So that is why, because else you would just stop here. To get the confidence interval, I need the square root of the variance or the standard error, and here it is. And you use the formula that's for simple random sampling without replacement. That's what we did to select. And there it is. And now we got this, and we're just going to substitute in there. So it's T hat, which I've just calculated, plus or minus twice square root of the variance. Can you see? Not hard. So it's, and if you work that out, it's between those two values. So you say you know that somehow the total number of acres under crop growth in the USA for that year is between those two values. Now say last year's amount was 984, da, 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 da. You could say, well, it could still be the same. Because this is between 8 and 10 with all these other digits. I don't really want to go into it. But if last year's total, the actual estimate, if it overlaps with this, you could say, well, we're not sure. But imagine if the two confidence intervals are far apart. Then you would say it's gone higher or lower or whatever. So that is how we think of it. The next thing I want to discuss is the effect of the sample size on your accuracy or precision. With other words, on the width of the confidence interval. Because remember, what are we trying to do? We spoke about this last week. You want your confidence interval to be as narrow as possible so that you can say, I'm sure, but I'm not saying like I'm sure, it's somewhere between 0 and 1 million. It's got to be like sensical. And that is why when you look even at this previous one, let's just go back here, can you see how big these numbers are? It's huge. But they're somewhere between the 8 and the 10. Can you see at least it's not between 1 and 45? So they have something. Now, what made it big or small? It's t hat plus or minus twice. Square root of variance is this thing. It's this. This thing is what's making it big or small because square root of variance is standard error. That's the same for both. That's the midpoint and that tells you how far to stretch it. So it's this standard error thing that's going to make it big or small. And that's what we're going to talk about next. You know you want your confidence interval to be as small as possible. And we said you're 95% sure always that your theta, your population value, this is the population value, is somewhere between theta hat minus twice standard error and theta hat plus is the upper end, twice the standard error. Okay, so that's just the midpoint. That doesn't affect the width of the confidence interval because that's in the middle. You go there and you subtract and you go there and you add. So the confidence interval, this affects the confidence in that can't affect the confidence, that just anchors it. Okay, so you think of it like that, theta hat minus and theta hat plus. Can you see that whether it's far away this point from this one and this point from this one, first of all, that will be the same length as that, obviously, because this is the same formula as that. Just the one time you're adding it and the one time you're subtracting it. Your theta hat can never affect the length of a confidence interval. Do you agree? That's just the middle. You go from there. How far to go will be dependent on this thing. And how far to go the other way will be dependent on that same thing. So it's always in the middle of your theta. And that could be, for example, a test question. Could be, does the change in does your theta hat affect the length of the confidence interval? So how the heck do I know? It's simple. Just think about what you do. You can see it doesn't. Because I want you to think about the formulas. So if you look here, that's your error. So you have the same length of error above and below the confidence interval, and you'll say I'm 95% sure that it's between the real theta value, because remember this is the estimate, the real theta value is between that and that. It's somewhere here. Okay? So your error is actually twice your standard error or square root of the variance of theta hat. That's what your error is, obviously. So now what we can say is if your thing you're interested in, first of all, let's just go back to the previous one. This is a general slide. It doesn't say I'm doing simple random sampling without replacement. It doesn't say whether you're doing what you're estimating. It's just got a theta. Theta is the thing in the population I want to estimate that's a constant. Theta hat is what I estimate it with. It doesn't say what type of sampling. This is true. Even if I'm doing stratified sampling, whether I'm doing systematic sampling, whether I'm doing with replacement, without replacement, simple random sampling, this will always be true. But I've shown you already whether I'm estimating Y bar in the population or T, this thing changes. It's little y bar or it's little ny bar, depending whether it's the total or the mean I'm estimating in the population. The thing you're estimating will determine your theta hat. The variance of the theta hat will depend also on the type of sampling. If I'm doing with replacement or without replacement, you saw those two columns didn't have identical things. So depending what you're doing, you would just look at that table I gave you just now, and then you would just know what would substitute there. Because I don't want you in the exam to be able to, or anywhere, to have a printout from a computer and you've got absolutely no clue where it comes from. If you don't know where it comes from, you won't know how to make it more accurate. And why it makes it more accurate, that you must understand. So in this case, let's take the special case now. So I'm going to take this previous idea, which is applicable to all types of sampling and all estimators. So I'm going to estimate in this particular case. The thing I'm interested in estimating is population mean. How am I going to estimate it? I'm going to estimate it with a sample mean. What am I doing? Simple random sampling without replacement and simple random sampling with replacement. I'll demonstrate both. So before you can give anybody a confidence interval or estimate, you must know what they want to estimate and you must know the method to select the sample because that affects everything. So it depends now. I'm doing simple random sampling, but I'm going to do without replacement as well as with replacement. What is your error? If you go back to that table I gave you earlier on, you will see this is the formula for the 1 over n, 1 minus n over n s squared is the estimated variance for simple random sampling without replacement, and that just becomes the, and if you look at this now, I didn't really want to. I want you to look at this now. That is your error. What is your error? Your error gives you a width of your confidence interval, doesn't it? What did I tell you all along? You're trying to be accurate. You're trying to make your confidence interval narrow. If you look at this formula, your error is what stretches your confidence interval. I don't want to be confidence interval. I can't say, and I want to be 95% sure that Z is 1.96. You can't do anything about that. Now you look at this, I want the confidence I want a 95% confidence interval, but I'd love it to be narrow. Okay? Can't change 1.96, that will stretch it as well, but that is what it is. I want to be 95% sure that's defined. Can I make my population bigger or smaller? No, it is fixed, isn't it? If I want it to be a narrow, the only thing I can work with is the n and the s squared. You can't change the s. The s squared is a variable because I select a sample and I work out, I've given you the variance of the y values, 1 over n sum y minus y bar squared over n minus 1. You select a sample, you work out the s squared. You can't say, you can't make it smaller than it is, but you work it out. A difference between samples, yes, it's a value. But of course, you can make your n, your little n, you decide. How many elements must I select? And that is what you have to look at this. And you say, if I would like my error to be small, which actually means my confidence interval to shrink, what you must do, you can make your n big. Look at that, 1 over n. This tells you you're dividing by n, but you're also subtracting the n. If everything else stays the same, making your n big is a good idea. Because that will make your error small, which makes your confidence interval small. You see? So what it's saying in the end, if you're lucky your s squared is small, that's nice because your confidence interval will be narrow. But usually what they do, you draw a sample and you work out the s squared. You see it's big. That's just a pilot sample. You take a few values, you say, oh, it looks like the s squared is going to differ a lot between this s squared is big. So then you say, I better take more samples when I really sample. So you often take a pilot sample, which means like a little practice sample. Say they're 300. They say, let's just take 30 values. And they had some clue and they said, oh, the s squared is very bad. The s squared and this one here. And I said, because it's so big, we better take more sample values because we're going to end up with a too wide confidence interval. So your s squared really is going to be big because that's how the values vary in your sample. If they're varying a lot in your sample, it must probably mean your population varies a lot. And when your population varies a lot, imagine you can't just have a small sample. Because then your sample things your different samples could have such different estimates. It throws everything out. It makes your confidence interval wide. So that is why we have to be very careful. Now, if you do with replacement, if you go back to that table I gave you, you'll see this is exactly taken from that. Z square root, and this is a square root of the estimated variance. You'll see it comes exactly from the previous table. S squared over N. And again, if you look at this, how would you make the E small? Well, obviously, if the S is small, it would help. Then your E will be small. But also if your N becomes big, because it's in the denominator. So both of those, whether you're doing simple random sampling with or without replacement, if you're estimating the population mean, you will always get more accurate results or better results. And it can shrink your error if your S squared is small or if your N is large. Okay, it's very important. And you can choose the N. I'm going to keep going so that you can have a little break at the end, and then we'll discuss just in general what you can expect in the test. So we're not far from the end, bear with me. The question is now, if you want this error, what is the error? It's the difference between the population value. Here I've used a Y bar U, but I really mean that to be, it can be thought of as the population Y bar. If you want that to be a certain value at most, what can you say? What can we do to ensure that my error is not too big? Okay, I've told you, you can choose the N. But now it's the other way around. Somebody says, you know, I don't want my error. I want my error at most to be this. What sample size must I get? And this is the question you very often get. People come to you and say, how many people must I select in my sample? Now, I've shown you in the previous case here. There is definitely a relationship between the error, with other words, your length of your confidence interval will be twice the error, because it's the error and the error. The confidence interval length, or the error when you're estimating, because it's in a confidence interval, is related to N. Now somebody comes to you and says, how many must I select? You can't just say 320. You've got to say, well, hang on, I can only tell you that if you tell me how much error you can live with. Now, what do I even mean by that? Imagine somebody that comes, a company makes 2-liter Coke bottles. They stamp on it 2-liter bottle. But the machines don't always give exactly 2 liters. So they want to know the population of all bottles. What is the real mean? And how much does it vary? They're trying to work this out. Then you say, and they say, okay, how many bottles must we sample? You say, well, let's just sample some. We measure them very accurately. You can't take all the bottles and open all of them because then there'd be no factory. So we're going to estimate by how much, what the average is for all Coke bottles in the country by selecting some, using some random sampling. Okay, we're going to do it like that. So now you say, they ask you the obvious question, how many bottles should we take? 300, 150? How will you even know? What you've got to say to the guy that's giving you that project, how much error can you live with? In other words, suppose the real population amount, the real population average for Coke in the bottle is 2.1. It's actually more than it should be. It says 2 liter, but it's 2.1. But when you work it out, your sample's not definitely going to tell you 2.1. There is a value, and your estimate, how much can your estimate be out? And he says it's still okay. Because you can tell him, I can never tell you, I'm not looking at the whole population. I won't be able to tell you exactly from our sample mean what is equal to your population mean. But how much can I differ by? And it's okay with you. And he might say, look, I'm working in liters. I'm working with 2 liters, so if I'm out by 5 milliliters, your answer for the sample B is 5 milliliters different to the real answer. It's still okay. So if you say 2.1, but it's actually 2.005, it's okay. But don't make it bigger than this. You see? He's got to tell you How much is okay? Because that's the error. The real mean and my sample's mean are not necessarily equal. He can't say, I don't care if you're out by half a litre. He's not going to be happy with that. That your sample mean is half a litre may be different to the real mean. You can explain to him, I'm going to have a sample mean that will give me some idea of what the whole population mean is. In other words, the mean amount that goes into a bottle, of a 2 litre bottle in the sample, I'll be able to tell you. But there's another number we don't know, that's a population real average. What you want to know is this value, most probably is different to that value. Even though you can make the two as close as you like, the closer you want them to be, the smaller the error, what's going to happen? If I want a very small error, what's going to happen to your M? It's going to shoot up. You can have a 0 error by making N equal to big N. I can give you no error. I can take all the bottles and really give you that average. But you don't want that one. So you've got to tell me my sample estimate. How close can it be to the real one? My samples mean to the real population mean, and you say it's okay. Does it make sense to you? But they must also understand the smaller the error they want, the bigger the E. The more bottles you're going to be opening. Okay? So that is why this concept, this error concept is very, very important. And so what you're saying, if you want your error to be smaller than some number, what would that N be and how can I calculate that? So usually people just talk about how many without thinking about it's going to be affected by the error. Okay. In my previous example where I spoke about maybe working out what is the total number of children under age 5 from parents that work at UKZN, you might say, okay, I'm going to have a Christmas party. I'm going to tell you how many children are in the sample, how many parents have the sample at UKZN, how many of all the people are sampled. I've got children under 5, I'm working out the total number. If I'm out by more than 3 children, it doesn't really matter because I want to put cake there. I want to know how much cake to bring for the little kids. But I must know how many children there are. It doesn't matter so much. If I'm out by 3, it's not going to matter. Or if I'm out by 30, I'm going to have computers there. I don't want to be, say, it's something where I want to know the total number of people coming and I'm going to take a sample and say, will you come, whatever. And each person coming is going to get an expensive gift. Then I say, I'm only going to be out by 1. It depends on the story. How much error you're prepared to live by. So you must look at the story will tell you won't know, it's the person that's coming to the statistician that has to tell you how much error they can live with. So what you're saying, and I think it's clear here, between the, in this case, population mean and the sample mean, the difference is the error. It doesn't, you'll see this modulus values. It doesn't matter the error whether you're 1 above or 1 below or 2 above or 2 below. Error just means there's a difference. It can be too big or too small. Because that's why it's a double-sided confidence interval. So what we're saying is, what at most can be the difference between the population value and the sample value? It can be between means. It doesn't really matter what the estimator is. So really what we're saying here, the error must be smaller than what? And you know from the previous slide, the error affects your sample size. The smaller the error, obviously, the more you're going to be. The smaller the error that the customer wants, the more you're going to sample. Now remember, suppose we said we work it out, and I'll show you in a minute how to do it. Suppose we do it and we say, you know what, to get that kind of error, you must sample 202, 212. But then they actually sample 230. The more you sample, the better. They can tell you sample at least so many, and if you feel like sampling more, it's actually a good thing. Just don't sample less. Okay? As long as you, because that's just the minimum amount. It doesn't mean if you say you must sample 120 and the guy says, well, I feel like sampling 140. The more, it means at least. It doesn't mean exactly that. So the example is a lovely example again. 3078 farms, taking up 300 farms in this particular case. And suppose in this case we're doing with replacement sampling. And what we take, now the error is Z squared over N. You'll see in the earlier slide, I just want to put it up right now. That is in the early, about 4 slides back. You can very easily see where that comes from. If you look at this here, you can see it's true. As you want the error to be small, your n is going to become big. Can you see that? Because your s squared will just be the variance within the sample. If you want this to be small, this better be big, because they're opposite. So you can see from there that when you're doing with replacement and you'll look in your grid and you'll very easily see, we did this in a slide back. So if you're given a maximum error, this is done by drawing a pilot sample, and that's important. A pilot sample just means not a real sample, because now we're saying your error, I'm going to use this formula here to calculate what my n must be. The person says, I don't want my error to be bigger than 3 children, the children example. I don't want the error to be bigger than this. Then you say, oh, okay, I know z is 1.96 or 2. S squared and n, I'm trying to find n. So this value, the guy coming to you will tell you what error he's happy with. 2 children or so many milliliters, whatever the story is. And you've got your n value. You want to work out the n. So you're going to solve for n. By squaring this side, and you can calculate the n, obviously. If you've got that formula, you know this is a 2, say, for 95%. You can easily from this calculate n, make it the subject of the formula, no problem, you can all do that. But what is s squared? Because they say, you must find the n. What is n? But to find n, you must have s squared. The s squared is the variance of the sample, but you want to know how many must I sample. So how can you look at s squared? You're saying, they're giving you the error, so this is known, that's going to be a number. You know that's 2 or 1.96. You're trying to calculate what n, but you don't know s squared because that's going to come from your sample. So you've got to sample to get it. You get it? So how can you sample and then work out what sample size you need? It's nonsense. So what you do is what's pilot sample. You say, with other words, let me just pick a few. No mathematical, nothing to do with how much error you have. I'm just going to pick a few. 36. Just pick a number, as many as you can. I've got a day, I can do 36. You use that, and it's called a pilot sample. It's not the real sample. But you use that to just guess roughly what your s squared is. Or you can say, we did the same thing last year, and I'm just going to use the s squared from last year. But you've got to get a value for your s squared. If you've got nothing to go by from the past, let's say the Christmas party for children. Last year we did it. This was our s squared because we already picked the sample. Because this is just to find out what sample size. We still going to go pick the sample. Last year's sample had this s squared. I'm going to use the same one. Or you're going to do a pilot sample. So then you work out by solving for n, which you can all do, that you know this value is 2 or 1.96. And you've got a pilot sample, you worked out you've got an s squared from your pilot sample, and they've told you, the manufacturer of the error has told you what error they're happy with. And now we're going to say there, so in this particular, the best way to show you this whole process, how you do it, and with other words, what we've said in the end, this is the way that we know what sample size to pick, because the s squared will come from your pilot sample, the manufacturer will tell you what error he's happy with, and you'll work out the sample size. So for this example, 3078, they picked 300. How did they know they must pick 300? Why didn't they pick 280 or 320 or 400? Because they did exactly what we've just said. How did they decide on the 300? They said, well, we're doing simple random sampling with replacement. The error in estimation must be less than 60,000. So whatever in agriculture department, government, minister, you don't have to worry how he found it. He said, I don't want to be out for more than 60,000 hectares. What does that mean, out? It means you're going to give me an estimate. I understand it's not the real value, but you better not be more than 60,000 out, the estimate and the real value. So you don't know the real value, you just get a sample. And what they're doing, they're capping the error. And that's going to tell you your sample size. As soon as you've capped the error, you can get the sample size. How do we do that? We've just said that your formula is what we just said, n times z squared, and you can see here s squared over e squared, and exactly like you can see here. In fact, what they did, they drew, and it's written up very nicely if you understand here. You don't know the s squared because you don't have a sample. You're going to draw a sample of 30 as a pilot. And it turned out that in that 30, only 29 farms saw. So one farmer didn't respond. He said, no, you can't come onto my farm. So out of the 30, they chose to be a pilot to work out the little s squared. Just a pilot, not the real s squared, to test, just to try and find out what n is. So they first took 30, just by their own choice, no reason to say 30. They worked out the s squared, and you see it sums up to sigma y up to n, yi minus y bar squared over n minus 1. And n should have been 30, but they only had y values for 29 of them, because the y didn't respond, and they were given this value. Using this, now that's my s squared. So your n is z squared, 2 or 1.96. And you use your s squared, there it is, over your error. Your error, he says, don't be up on more than 60,000. Can you see where that comes from? It's really, it's hard to do it here because I don't have all the other sides, but really it's straight from the previous one. What is this saying? So what we're saying in the end, you know what? We did, the guy said don't be up on more than 60,000. I took a pilot sample of 30. I calculated s squared from 29 of them because one didn't respond. I found s squared to be that, not the real for the sample, it's just my pilot sample. I threw it away. Then, once I knew that, I just put that into the formula and I said 288. What it means is if you want to estimate, like we do here, to work out the total, using simple random sampling with replacement. This is the formula that links. We've got a formula that links error and n. And we solved for the n, and we said, putting all that in from our pilot sample, which had 519085 as my s squared, I work out n is 288. But I had to have a pilot sample, and I had to know 60,000 is the maximum error he's happy with. And I said, you better sample at least 288. It doesn't mean equal to 288. At least 288. What did they sample? 300. That's good. 300 is more than 288. Why is it good? Why did he listen to me? Because maybe he said, I've got time to do 300, or he just did it. You just said, don't stop, because he's got a few people going to farms, and he made sure they went over 288. When he stopped them already, they did 300, whatever the story is. As long as it's not less than 288, everything's fine. Because you know also from our earlier formula, I can go back to this. You know from one of the four, here, we're doing simple random sampling with replacement. This is what I use to work out the n. You just solve for the n. What does it say? Your error will go down as n goes up. He's just said, I don't want to be out more than 60,000. And you calculated n must be 288. He took 300. So that means his n has gone up. Well, obviously, your error must be at least 60,000. For 288, I can expect an error of 60,000. So if I take 300, the error will be even smaller. You see? So that is why it's good to take a larger n. That just gives you a minimum value. So let's just go back to where we were. And there's a story of that. So if we do a simple random sampling with replacement, at least 288 farms, and so on, to get an error of no more than 60,000 acres. We saw that we picked 300, but 288 would have been what you needed. The more you take, the better. And so on, the whole story is there. So as we say, you don't want to be out more than 60, but the important thing is to understand that he took the important thing to understand is that he took a pilot sample to be able to do that. Now, I can go on and do coefficient of variation, but I can see that people's eyes are glazing over. So should we take a break? And I don't know if you need a bathroom break or whether I should just go.